Welcome back to the Daily Dean. Why is the sun so freaking bright all the time? That's an excellent question, and I'm going to be giving you all the information you need to understand why, hopefully. So you can basically call this a sun rundown, basically. Now, first of all, first thing out of the way, the sun and everything in our solar system first came from a giant cloud of gas in space. Clouds of gases in space are called nebulas. So we had a nebula that became our entire solar system. And at the center of the gas that started contracting, because the gas had to contract in order to become our solar system and whatnot, we have the sun at the center, the core. Now you may be thinking, wow, so I guess the matter in the gas was pretty evenly split up. But not really, because the gas in the middle was more concentrated and is where all the mass in this nebula combined. So as a result, 99%, over 99% actually, is inside of the sun. Like, over 99% of the mass in the solar system is inside of the sun. So imagine everything around you right now. All the places you've seen on Earth, everything in your room, you even, all that stuff all that stuff only makes up less than 1% of the solar system. Everything else, even the Earth, is just, a fraction of a percent. And everything else is inside of the sun. And all that stuff means that there's a lot of gravity. Gravity built up with all that mass, because mass creates gravity, or mass attracts everything in the universe, and all that mass is pushing down and wants to collapse into itself, because the gravity, right, attracting itself to the center, where most of the mass is concentrated. Now, because all this mass and all this gravity is pushing towards the center, we have a lot of pressure inside of the core of the sun. The core of the sun, a lot of pressure means that the atoms and the nuclei and all the junk and hydrogen, because the sun is made up mostly of hydrogen, the element, all that stuff is being like tossed around super duper fast and whatnot. And because it's going super duper fast, when they smash together, you actually end up fusing the atoms together. Now think about fusion as, welding, but instead of welding, it's literally jamming something into another thing at like millions, I think. Maybe not millions, but really, really fast speeds. And so when they combine, like when hydrogen combines into helium, that's the fusion of hydrogen to helium, it releases some energy, because you need 4 hydrogen atoms to create 1 helium atom. Now, what's interesting is that when you add up the masses of 4 hydrogen atoms, you actually have, you would predict that it's at least the amount of mass in the helium atom, because the helium atom is made up of 4 hydrogen atoms, right? So when you add it up, you predict that it's going to be like, two units or whatever, or just as an example, and the actual result is actually closer to 1.95, and you think, wow, so the actual measured mass of the helium atom is only 1.95. Where did the 0.05 go? Well, it actually got released as energy, and the energy is what's radiating from the sun and makes it so bright, because that happens all the time in the core of the sun, fusing together hydrogen in the hydrogen proton chain or whatever, and becoming helium. And all that energy has to travel through the layers of the sun. This is a neat little fact. Travel through the layers of the sun through, radiation zone, the convection zone, and the corona and whatnot. Oh, coronavirus. No, it means that it's the little, it's like the atmosphere, kind of, the outer layer of the sun. And as it travels through the layers, one neat little fact is that the irradiation zone it actually takes the light and the energy from the core. It takes millions of years in order to exit out of the radiation zone, because it's bouncing around. And if you imagine, if you went in a straight line, boom, the light's going to go straight out. But because it's bouncing around, its trajectory and its path is always changing, which results in it taking a longer path and taking much more time, millions of years even, just to get to your eyes. So think about that. Light took millions of years to reach your eyes because of how long it takes to bounce around and travel through the core of the sun, or the innards of the sun. And now, all that is radiating away from the surface of the sun, which we see as visible light. Well, technically radiation. The sun emits lots of radiation, which you can see through telescopes and special computers and whatnot. But everything from the sun is once again getting blown away. and and it actually causes an equilibrium between gravity and fusion. Equilibrium means that gravity wants to contract it. It wants to reduce that crap into the smallest spaces it can. And as it tries condensing it, it'll actually end up, it doesn't, because the fusion fights against it. Imagine like fusion is releasing all this energy. If all that energy wasn't being, held together by the gravity by the mass of the sun, it would just shoot everywhere, and we would see a freaking nuclear bomb going off from our side, from our vision on Earth. But why don't we see nuclear bombs going off on the surface of the sun? Because that happens in the core, and the core is being contained by gravity, and all that gravity is preventing the sun from, 1, collapsing in on itself, and 2, expanding out against itself. So that's a little fact there. There's a constant anime battle between gravity and nuclear fusion in the core of the sun, and ain't that fantastic? I hope you enjoyed, and I hope you learned something, and I hope you have a wonderful week. Bye.